Good afternoon, dear students.
Good afternoon, sir.
So, how are you all?
Afternoon, sir.
Good afternoon, sir.
Afternoon, sir.
Are you fine?
Yes,
Yes,
sir.
sir.
Yes, sir.
So, your classes are going on smoothly?
Yes, sir.
Okay. So, did you watch the last video I shared about the first law of thermodynamics?
Yes, sir.
So, I think I need not have to repeat that same actually topic, but just we will recapitulate what we have learned. So, I am presenting, I think my screen is visible to you. Okay. So, basically, the first law of thermodynamics uh, it deals with the transfer of heat and work. So what it says basically, so in a cyclic process, so numbers of processes will be there. So in each of the processes, so there will be transfer of heat as well as there will be transfer of work. That means the transfer of energy will takes place. So in a cyclic process, whatever be the summation of work will be equals to the summation of heat. So mathematically, if you want to write that same first law, then you need to write like this way. Circular integration of delta Q is equals to circular integration of delta W. So for these two processes which compose to a cycle, so in the figure it is easily visuable that in going from 1 to 2, that is one process, and from 2 to 1, that is another process. As because the initial state is equals to the final state, so this is a thermodynamic cycle. So here in this cycle there are two processes, 1 to 2 through part A and 2 to 1 through part B. So the total heat interaction in this cycle is QA from 1 to 2 and QB from 2 to 1. So by this first law, so we will be able to write that will be equals to summation of the work transfer. Means in this part, whatever be the work transfer, WA1 to 2, and whatever be the work transfer in 2 to 1 through part B. So here I have not written the sign convention. I have not followed any sign convention. So all of you know that when it is delivered from the system, so then it is positive, and what is given to the system, work is given to the system, so it is negative. So just like that, your heat, so when heat is given to the system, it is positive, so the sign is reverse actually, and when heat is evolved from the system, so we will consider it to be negative, just like exothermic reaction. Okay, I think this point is clear to you. So when you will apply the same concept and you are going to find out, so what you will get, so you will get that the difference, finally what you will get by putting in this equation, that the difference in between these 2 points 1 and 2, no matter through which path you will go, the difference is equal. Means delta Q minus delta W through A path and delta Q minus delta W through B path, this will be equal. So that means some energy it is stored in this system in going through any of the path, whether it may be A, B, C, D, any path. So that amount of energy which will be the difference in between these 2 points will be one constant value, and that value is said to be the energy. Okay, the total energy of the system. So that thing it is written theoretically here. Since A and B are arbitrarily chosen, the conclusion is, as far as process concerned A and B, the difference del Q minus del W remains a constant as long as the initial and the final states are the same. The difference depends only on the endpoints of the process. Note that Q and W themselves depends on the path followed, but their difference does not. Okay, because while you will be going through the paths, the value of Q and W will be different, though the final point and initial point are same. Okay, that is why the Q and W, those are called as path functions, not the point functions. Means by directly subtracting in between these points, you will not get the value. Okay. So if you just want to apply the first law of thermodynamics for a cycle, then it will be del Q minus del W equals to delta E or dE. Okay. So D is E2 minus E1. D is the difference of the energy. So this energy consists of basically three components. One is the internal energy, which is denoted by capital U, then kinetic energy and the potential energy. So I have told you in the last class that effect of this internal energy is more in comparison to kinetic energy and potential energy. Means these two terms can be neglected. Okay. Or you can write the whole term, okay, in terms of E. So for any process, so earlier we were writing for cycle, now for any process. Okay, so earlier 1 to 2 was one process, 2 to 1 another process. So I have considered here only 1 to 2, that is part A. So for this part, if you want to write the first law of thermodynamics, then the difference of this heat and work Q minus W will be equals to what? One, energy, okay, which is constant throughout any part in between this point 1 and 2. So that energy is E2 minus E1. Okay. And for part B, 2 to 1, so this is Q minus W, E1 minus E2. So E1 value is greater, that is why E1 is written earlier. Okay. So for any cycle, you need to write like this. For any process, you need to write like this, because thermodynamic cycles are composed of numbers of cycles. So for each of the cycles, so we will be writing this equation. So you should know how to write this equation for any process. Okay. So for any process, we will be writing the values Q minus W will be equals to delta E. Okay. So E2 minus E1, or it may be E1 minus E2. So that same thing it is written. So here, as I have told you, that Q will be equals to delta E plus W, as because U component is having more influence on E term, internal energy term is having more influence on E term in comparison to kinetic energy and potential energy. That is why I have written here delta U. Okay, instead of delta E, I have written here delta U. So some problems we will be solving, but before that, so we will see, yeah, one very important thing. This thing you need to commit to your memory, okay, before you are going to solve any problem, numerical problem. So heat, what is heat? So heat is basically one kind of energy. Its unit is joule, isn't it? So it is a path function. We have seen that heat is a path function. So to define the heat, we have to categorize this heat. One is the specific heat. So what do you mean by specific heat? So specific heat, it is the amount of heat which is required to raise the temperature of a unit mass substance through unit degree centigrade. That is called as the specific heat of a substance. Okay, so for different substance, the specific heat is different. So again, I am telling the definition that the specific heat of a substance is defined as the amount of heat required to raise a unit mass of the substance through a unit rise in temperature. This may be in Kelvin, this may be in degree centigrade. Okay, so for unit mass of a substance, if you want to raise the temperature by unit degree or by unit amount, that temperature is called as specific heat. Okay, so the symbol of the specific heat is denoted by capital C. Okay, capital C. You need to remember this one, capital C. So its definition is Q, because this is specific heat. So specific means what? You need to divide this by small m. Okay, because unit mass. You need to rise the temperature of a unit mass substance to unit degree. That is why the total heat will be divided by the mass and the temperature. Unit mass and unit degree rise in temperature by this definition. That is why mathematically we will be writing it like capital C will be equals to capital Q upon M. M stands for mass into delta T, change in temperature. So its unit is joule per kg into Kelvin. Okay, so Q, because it is a form of energy, Q equals to joule, M is kg, SI unit is kg, and delta T means difference of temperature will be also the unit of temperature, that is Kelvin. So joule per kg Kelvin. So it is a unit of specific heat. Okay, so there are other two types of specific heat. So if you divide the specific heat, so one will be specific heat at constant pressure and specific heat at constant volume. So we will define that one also shortly. Okay, so you should remember this point. Okay, this definition of this specific heat. Okay, so heat is basically denoted by capital Q. So specific heat is denoted by Q by M into delta T, because unit for unit mass substance and unit degree rise in temperature. That is why it is divided by M into capital delta T. Okay, so this is specific heat. Yeah. So I have told you that when you will divide this specific heat, so you will get two specific heats. One is the specific heat at constant volume, another is the specific heat at constant pressure. So first we will define what is specific heat at constant volume. So this specific heat of a substance at constant volume is defined as the rate of change of specific internal energy, because internal energy is defined by what? Capital U. Okay, so when we have studied the intensive property and extensive property, I have told you that these properties are basically denoted by capital symbol. Okay, and the specific properties are denoted by the small letter symbol. Okay, so the capital U will stands for the heat. Okay, sorry, internal energy, and the specific internal energy will be denoted by small u. Okay, so this Cv is denoted by specific heat at constant volume, is denoted by the ratio between the change of specific internal energy to the temperature, change in temperature when volume is constant. So as because it is specific heat at constant volume, so volume is constant. So here volume will be the suffix in this mathematical expression. Okay, so since here two things are missed, U, internal energy and temperature are the property of a system. Here U and T, okay, these are the property of a system, isn't it? So temperature is the property of the system, that is Cv is a property of the system. Okay, so Cv is the property of the system. So specific heat at constant volume will be the property of the system. Okay, so you should commit to this memory, this definition. So the specific heat at constant volume of a substance is defined as the rate of change of specific internal energy, small u, delta small u, with respect to temperature when the volume is held constant. So here the volume is constant. Okay, so this is the definition of specific heat at constant volume. So this heat transfer at constant volume increases the internal energy of the system. Okay, so when heat transfer at constant volume takes place, suppose if you take the example of the simple piston cylinder arrangement, suppose some gas is confined in the cylinder. So if you just heat that gas without expanding the boundary, means without expanding the piston of the cylinder, then what will happen? The internal energy of the system will rise. Okay, that is what actually means. Okay, then you need to define one very important term, that is enthalpy. Okay, so enthalpy. So when we have studied the types of properties, then we have found this word enthalpy. So this enthalpy of a substance H This enthalpy is actually denoted by capital H. This is specific enthalpy. That is why it is denoted by small h. Okay. So if you want to define the enthalpy by taking capital H, so H will be equals to capital U plus capital P, capital P. So here I have defined it by using the specific terms, because specific terms you have to denote it by small letters of the alphabet. Okay, so here small h will be equals to small u plus pv. Small u is what? Internal energy. Small p is the pressure. Small v is the volume. Okay, so enthalpy is defined as the summation of internal energy and the product of pressure and volume. So enthalpy is an intensive property of a system. Okay, so this enthalpy is an intensive property of a system. Actually, specific enthalpy is an intensive property of a system. So heat transfer at constant pressure increases the enthalpy of the system. Okay, so heat transfer at constant volume increases what? The internal energy of the system. But heat transfer at constant pressure will increase the enthalpy of the system. That is why this term is very, very important. Okay, because in a system, somewhere in some mechanical system or thermodynamic system, what you will get? You will have to heat the substance or the system by considering the volume to be constant. It is not increasing or it is not decreasing. The total volume will be constant. The system boundary will not expand. So in that case, when the volume will be constant, if you add heat, then it will increase the internal energy. Okay, means molecule will be colliding randomly, isn't it? When the space is confined, when the space is, you are not giving any space to expand the boundary of the system, what will happen? The molecules will collide due to the increase of kinetic energy. Okay, so the total internal energy of the system will increase. Okay, but when you are allowing the volume, means you are expanding the system but you are not increasing the pressure, then what will happen? The enthalpy of the system will increase. Okay, so this is very much important, these two lines. That is why they are written in bold letters. Okay, so enthalpy is an intensive property of a system, and heat transfer at constant pressure increases the enthalpy of the system. And how will you define the enthalpy? So enthalpy is basically, this is specific enthalpy. Okay, because I am writing here small h, so specific enthalpy will be defined as the summation of, because here plus sign is used, summation of the internal, specific internal energy and the product of pressure and specific volume. So if you are defining the specific enthalpy, but when you are defining the enthalpy, so it is the summation of internal energy plus the multiplication of pressure and volume. Okay, so here specific enthalpy is an intensive property, but enthalpy is an extensive property. Understood? So it is dependent on the mass of the system. Understood? So you need to commit to your memory this formula. Okay, this formula and this formula, H equals to U plus PV. So here these two lines are very, very important. Specific is a constant volume, and when you are increasing the temperature of the substance, or you are just supplying heat to the substance by considering the pressure to be constant, then enthalpy of the system will increase. Understood? Then next comes the other type of specific heat, that is specific heat at constant pressure. Okay, so specific heat at constant pressure, Cp, because specific heat is denoted by capital C. Cp is defined as the rate of change of enthalpy, rate of change of enthalpy with respect to temperature, or you can write rate of change of specific enthalpy. Okay, because here I am writing small h, so rate of change of specific enthalpy with respect to temperature. Okay, so when the pressure is held constant, so here the pressure is constant, that is why it is written as suffix. So you can write P equals to C also, because pressure is constant, or if you will write P as suffix, so it means that the pressure is constant. Okay, so this is the definition of specific heat at constant pressure. Okay, so one very important relation in between the specific heat at constant pressure and constant volume. So relation between, actually this is the relationship between Cp and Cv. So Cp minus Cv will be equals to R. Okay, and this R is called a specific gas constant. Okay, and you know the value of this universal constant, that is 8.314 joule per mole into Kelvin. Okay, 8.314 joule per mole into Kelvin. So you need to remember this value. Okay, so Cp minus CV will be equals to capital R. So in some of the numerical problems and in some of the derivations, so we'll be using this expression. So you need to remember, okay, today's lecture we have defined so many terms, isn't it? 3-4 terms. So you need to write all these things distinctly, and you need to just commit to your memory all these points and formulas. Understood? Okay, so we will not move to the next topic. Then we will see another topic which is related to the PDB work. We have we started, but due to some pending work, so I was not able to complete that lecture. So today we will I will going to complete that part. Okay, so that is very actually important point of view, okay, for exam point of view for you. Okay, so see, the earlier we used to calculate the PDB work or the displacement work for various quasi-static processes. Okay, so I told you what is a quasi-static process. So a quasi-static process is a process so which happens slowly, okay, and each of the points which is a part of the process so will be a thermal equilibrium point. Okay, that means by attaining thermal equilibrium points, number of thermal equilibrium points, so the system will uh, reach the state 2, okay, the second state, okay, or the third state or the fourth state. So just like that it will attain the states. So when constant for constant pressure process, so we found out the work done by the same formula because it is a PdV work, okay, or displacement work. So why it is PdV work? So I have told you in one lecture. Okay, so if it is clear to you, then you will be able to understand why the displacement work is denoted by integration of PdV. Okay, so if constant pressure process is there, that means what? Volume is variable, means volume dV is existing. So if dV exists, means there will be some definite value. Okay, so pressure is constant. So for constant pressure process, so if you want to draw the curve, so it will be a constant pressure process from 1 to 2. Okay, and this plot is in between P and V because we are concerning only on P and V. Okay, so this is P axis, this is V axis. So from 1 to 2, the area under this curve will give you the total work done. Okay, so that is why these are hatched. Okay, some inclined lines are drawn, hatched lines are drawn to show the area. That is why it is written as W1 to 2. So earlier the volume was V1, now the volume is V2. So you can take the example of your piston cylinder. So suppose in one state 1, when the piston occupying, when the gas occupying and in the cylinder, volume of the cylinder, so that state is denoted by V1 and P1. Okay, pressure is P1 and the volume is V1. Now the, let's say, some heat interaction or work interaction is occurring on the system, and the volume is expanded to V2 and the pressure is expanded to P2. Okay, so because the pressure is constant, okay, so you cannot change the pressure, it is neither increasing nor decreasing. That means in a constant line, it will follow a constant line. So for this process, so if you want to apply the PdV work, then it will be P V2 minus V1 because pressure is constant. So mathematically you can write, so P here, so for dV you will be writing V2 minus V1. Okay, so capital V2 minus V1. So now you can find out the value if it is given. If the value of P1, P, V2 and V1 are given, then you will be able to find out W1 to 2. Okay, for this constant pressure process. So two things actually for 1 to 2. So we have seen that one first law of thermodynamics can be applied. Okay, then this is the calculation part, that we can calculate the work done. Okay, from going from point 1 to point 2. Okay, so these are two different things actually. So work done can be calculated. So if you just want to find out the work, if you are able to find out the work done, and if your heat uh, transfer it is given, Q value is given, then you will be able to find out the internal energy because by applying the first law of thermodynamics. Understood? Now the constant volume process. So constant volume process means what? Volume is not changing, but pressure is changing. So pressure is decreasing from 1 to 2. The pressure is decreasing. Okay, here it is P1 higher value, P2 lower value. So as arrow mark is given in this direction, so pressure is decreasing. Okay, so volume is constant. So for this type of process, so there is no change of system boundary or displacement work. That is why the work done will be 0. Understood? So for this type of process, if this graph is given to you and you are asked to find out what is the work done, then you need to put it here, the value, you need to put it in this integration of PdV. So dV means what? The change of volume. The change of volume is 0. Okay, so that is why it is 0. Now other types of quasi-static processes are there, that is isothermal process. So earlier we have studied the work done for constant pressure process, constant volume process. Now when the temperature is constant, then what will be the work done? So when temperature is constant, the relation between P and V is constant. So P into V will be constant. This is not specific heat, this is constant. Okay, C is constant. So work done is given by this formula, V1 to V2 PdV. So you have you can write PV equals to what? P1 V1 plus P equals to P2 V2 equals to P3 V3. Just like that you can write. So here this PV equals to P1 V1, or you can write P1 V1 equals to P2 V2. That is also correct. So that ratio or that that digital value, that value will be will be constant. Okay, so PV equals to constant. That means this process is isothermal process. Okay, so this P, small p, will be equals to what? P1 V1 divided by capital V, isn't it? So mathematically you can write small p will be equals to this expression. Okay, so now what I will do, so instead of this small p, I will be writing this term P1 V1 by V. Okay, so P1 V1 by V dV. So integration of dV by V means integration of 1 by V into dV is what? Ln V2 by V1, isn't it? Because lower limit is V1, upper limit is V2. So if you do the integration of 1 by x dx, then it will give you ln x. Okay, ln x, exponential logarithm x. Okay, ln, so x ln V. So lower limit is V1, upper limit is V2. So P1 V1 it is constant, so ln V2 by V1. Okay, so instead of V2 by V1, what you can write? P1 by P2. So P1 V1 ln P1 by P2. So you can write this expression or this expression, but the thing is that, so you need to know what is a isothermal process. So in isothermal process, the temperature is constant, the volume may change, the pressure may change, and the mathematical expression for isothermal process is PV equals to constant. So if you are asked to find out what is the work done for isothermal process, so you need to do this calculation, okay, in this way. Understood? This is very easy. Only you need to remember what is the integration of 1 by V into dV, means dV by V. It is ln V. Okay, ln V. Ln is what? Exponential logarithm. Okay, ln V. As V1 and V2 are the lower limit and upper limit, that's why I'm writing here V2 by V1. Understood? Okay, so now the next process is polytropic process. Okay, someone it is said as the adiabatic process, but in adiabatic we will be writing uh, gamma instead of this n. Okay, so what is actually n? N is the atomicity. Okay, atomicity. N is called the atomicity of the molecular gas. Okay, n is the atomicity. So PVN equals to constant. PVN equals to constant. Understood? So that process is the polytropic process. And PV gamma equals to C will be an adiabatic process. In adiabatic process, there is no transfer of heat, but there may be increase in heat. Okay, so this polytropic process, here PV to the power n will be equals to P1 V1 to the power n, P2 V to the power n equals to constant, because I can write by introducing suffix 1, P1 V1 to the power n equals to P2 V to the power n, just like this expression. Okay, so just like Charles law and Boyle's law, you can write like this way. So for P, I can write P1 V1 to the power n by Vn, isn't it? So this Vn will go to this side. Okay, bottom side, P1 V1 to the power n divided by P to the power n. So in the PdV work, so we will be putting the value of P, small p, by this value. Okay, so when you will be putting this P value by this value, okay, which you have got by this relation PV to the power n equals to C, so you will get this one. Now you need to find out the integration, because P1 to the power n will come out. Okay, so dv by v to the power n. Okay, so what will happen? So means v to the power minus n dv. Okay, so v to the power minus n plus 1 divided by minus n plus 1, and lower limit and upper limit you need to write. Then when you will simplify, so you will get this expression. Okay, after simplification, when you will be putting the v2 value and v1 value, upper limit minus lower limit, then you will get this expression. Okay, so this expression can again be written by multiplying this into this minus this into this, so 1 minus n. So after that, after simplification, because v2 term is there, v2 term is there. Okay, so n will be cancelled out. P2 v2 v1 to the power n, p1 v1 to the power 1 minus p2 v2 to the power 1, so 1 it is not written here, so n minus 1. So from this, so you can write this expression in this form: v1 v1 n minus 1 divided by n minus 1. Then after simplification, you can write this expression in this way. So this is a very simple mathematical calculation. Only by taking this p1 v1 upon n minus 1, so you will be able to, because 1 will be remain there, and this term you can write like this way. Understood? So if this is an adiabatic process, so it is a polytropic process. Okay, so if this process is an adiabatic process, so how this one will happen, how this expression will be look like actually. So actually it is very simple. So in adiabatic process, only you need to replace this n by gamma, because I have told you that n is the atomicity. Okay, n is the atomicity of the gas or molecule. Okay, so for your convenience, I am just telling you that the relation between n and gamma, okay, n and gamma, is gamma equals to 1 plus 2 upon n. Okay, so gamma equals to 1 plus 2 upon n. So this is when n will be written, it is polytropic process. If gamma is written, then it is an adiabatic process. So pb to the power gamma will be equals to constant. Okay, and where gamma is what? Cp by cb. So this is also an important relation of this cp and cb. So the ratio of the specific heat and constant pressure to the specific heated constant volume will be equals to gamma. Okay, so gamma is it is the for monoatomic gas. So the value of gamma is 1.67. This gamma value is 1.67 for monoatomic. For diatomic gas, this value is 1.4. Okay, for triatomic gas, this volume of gamma will be equals to 1.33. Okay, 1.33, and the relation between the gamma and n is gamma equals to 1 plus 2 by n, or 2 upon n. Okay, actually that n is the degree of freedom of the gas molecule. Okay, so the same expression for adiabatic process, because earlier it was pv to the power n equals to c, now it is pv to the power gamma equals to c. So the derivation is not shown here because it is same. Okay, only you need to replace n, small n, by gamma. Understood? So you'll get the same process. Now if you want to plot it in a pv diagram, okay, this is isothermal curve, because pv equals to c, and this is quasi-static process. Okay, so isothermal curve will be look like this. So where it will be look like this, when you will be plotting the values in between p and v, so you will get the curve to be this one. From 1 to 2 you will get a you can say parabolic. Okay, this is parabolic or any exponential curve, or okay, so this is this curve, this type of curve you will get, an area under this curve will give you the work done, w1 to 2. Understood? So this is the curve for isothermal process. Okay, so if you want to plot all the processes PV to the PV it is equals to 1. When L infinity means what? So we will be having some value, okay, definite value. So it will be having a constant value, okay. So this line will give you the value of n equals to infinity, okay. And these are the lines which are drawn for different values of n. So if n equals to 1, so PV equals to C, means isothermal curve. Isothermal curve, PV equals to C. Understood? So this curve is similar to this one, 1 to 2. Then if n equals to 2, so it will be little bit downside, okay, to this curve. And if n equals to 3, then again it will be just shifting, okay, a little bit downside to the earlier curves, okay. So if you increase the value, so you will get uh, a, a straight line, okay, just like this finally, because from here it is increasing and you will get a straight line finally when n value will be infinity. So here it is written process in which PV n equals to constant, okay. So I think this is sufficient for you for today's lecture. So all these things, whatever we have discussed in today's class, are actually some important form relation, important terminology, specific heats at constant volume, specific heat and constant pressure, then enthalpy, then gamma, Cp minus Cv equals to gamma, or Cp by Cv equals to gamma. So these are the some important relation. Then what we have done, so we have found out the PDB work, displacement work for various processes, isn't it? So that is very, very important. So different for different quasi-static process, what are the different works which will be done by the system, or what will be the work done in each of the processes. So we need to find out. Okay. So dear students, so thank you for watching this video. So if you have any doubt, so you can ask. Okay, so I think these concepts will be clear to you only when you will watch this video again. Okay, so today it is not possible for me to upload, so tomorrow I will be uploading in the college because I am at home now. So tomorrow I will be uploading it and you all just go through it, because these uh, things, okay, these topics are the parts of your class test 1. Okay, your class test 1 will begin from 10th, so these things will be there actually. Okay, so you have to be prepared. Okay, so just go through the lecture when it will be uploaded, and you just you just watch the previous lectures whatever I have uploaded. Okay, and you, as I have told you earlier, that you follow, you just consult one good book, okay, as well as some video lectures also. Okay, though you are watching my videos also, sometimes it may not be understandable. Okay, so for some of you, so some in Hindi lecture also some good videos are there, okay, in YouTube. Okay, so if you just if you are okay with those videos, then also you can watch, but those sources should be genuine. Okay, some good coaching centers are also delivering some good lectures. Okay, so you can follow those, but basically thoroughly you need to study, because in graduation you need to study thoroughly. Okay, so basically the coaching centers, whatever videos they are actually uploading, few videos are actually they are directly meant for solving problems. Okay, so in shortcut they are actually make you understand all those things. So better you just try to follow my lecture. Okay, so thank you. So if you have any doubt, so you can ask now. If you don't have any doubt, then you